All right, let's dive straight into this explainer and equip you with the fundamental physics toolkit you need to describe the real world. And don't worry, we're completely ditching the dry textbook language today. Look, if you've ever felt like physics suddenly turns into this weird alien language the second you step into higher-level mechanics, you are absolutely not alone. The secret here? It's not that the math is impossible. It's just that you need to grasp the visual language that actually maps our physical reality. So today, we're going to break down the mathematics of motion, forces, and reality itself by totally mastering the language of vectors.
So here is our roadmap for today. We'll kick things off with scalars versus vectors, look at the anatomy of vectors, tackle the rules of addition, break them down into components, and wrap up with vector multiplication basics. Let's get to it.
Picture this scenario. If two of your friends pull you in completely opposite directions, but with the exact same amount of force, where do you go? Well, nowhere, right? You stay perfectly, completely still. This perfectly illustrates that just knowing the magnitude of a force, like how hard they're pulling, without knowing its direction, simply isn't enough. If force was just a regular number, 10 units of pull plus 10 units of pull would equal 20 units of movement. But the real world has geometry. Direction literally dictates reality.
Section 1. Scalars versus vectors.
Think about it like this. Eating 4 kilos of gulab jamuns. That is just simple scalar math. But being pulled by your friends to go to a tea stall versus going to play a game of Coco, that requires vector math. A scalar is literally just an amount. Things like mass, time, volume, those are scalars. 4 kilos of sweets plus 4 kilos of sweets is always going to be 8 kilos. Simple addition. But a vector has magnitude and direction. If one friend pulls you toward the tea stall with 10 newtons of force and the other friend pulls you the opposite way for Coco with 10 newtons, you don't suddenly experience 20 newtons of movement. The forces directly oppose each other and cancel out to zero. That's the magic of special vector addition.
Let's say you walk 4 meters perfectly straight forward, and then you take a sharp 90-degree turn and walk 3 meters to the left. Your total distance, which is a scalar, is just 4 plus 3, so 7 meters. You physically took 7 meters worth of steps. But your actual displacement, the vector representing your exact change in position from where you started, that's just 5 meters. You didn't invent some crazy new math to figure that out either. You just busted out a right-angled triangle. Vectors really just give a mathematical structure to things you intuitively already know.
Section 2. The anatomy of vectors.
Okay, so when we map this stuff out visually, like representing Champa and Champak racing, a longer arrow simply means a faster velocity. We draw vectors as simple arrows. The line itself, starting from the tail, is the magnitude. So a massive 100 Newton force gets a super long line, and a tiny 5 Newton force gets a short one. The arrowhead points the direction. Oh, and just to throw a quick vocabulary word your way, when a bunch of forces are acting on the exact same flat 2D surface, kind of like ant trails zigzagging across your kitchen floor, we call those coplanar vectors.
Now, writing out 10 newtons in the x-axis direction every single time gets really tedious for physicists. So they came up with unit vectors. You'll see these written as the letters I, J, and K with these little hats or caps sitting on top of them. Because their mathematical magnitude is exactly 1, you can multiply any number by them and it doesn't mess with the value at all. So 10 I caps simply means 10 units perfectly aligned along the x-axis. It's a really neat, elegant little shorthand.
Just like taking a road sign and moving it further down the street doesn't actually change the direction it's pointing, you can slide vectors around a graph all day long as you keep their length and their angle identical. This is, hands down, the absolute most important conceptual trick in this whole explainer. You're totally allowed to pick up an arrow on a graph and move it anywhere, as long as it stays parallel to where it started. You aren't changing its fundamental meaning. And this freedom to slide them around, that's exactly what lets us line them up and add them together.
Section 3. The rules of addition.
So how do we actually combine these arrows when multiple forces are happening at once? Well, instead of getting intimidated, just treat vector addition like a visual puzzle. Say you've got 2 forces. Remember our trick about sliding vectors around? Just take one vector and slide it so its tail sits perfectly on the tip or the head of the first one. Then just draw a brand new arrow connecting the very first tail straight to the very final head. This makes a triangle, which is why it's called the triangle law. That brand new third arrow, that's your resultant vector. It's the grand total of your combined forces.
Okay, but what if your friends are pulling you at some weird, wonky 120-degree angle? When things are at a perfect 90 degrees, we know we can just rely on the Pythagorean theorem. But let's be real, the world is messy. Forces come at you from 37 degrees, 53 degrees, or completely obtuse angles. So how on earth do we handle that?
Don't let the math here overwhelm you. This formula is actually just the Pythagorean theorem on steroids, built to handle literally any angle you throw at it. Your resultant, r, equals the square root of a squared plus b squared plus 2ab cosine theta. See, if the angle theta happens to be 90 degrees, the cosine of 90 is 0, so that whole trailing part just vanishes, and boom, you're back to classic Pythagoras. But for any other angle, this mathematical workhorse just gracefully stretches or squeezes your triangle to give you the exact magnitude of the resultant force. It's pretty brilliant.
Section 4. Breaking vectors into components.
Sometimes using that resultant formula gets super clunky, especially if you have like 3 or 4 forces acting on an object at once. So here's an incredibly powerful trick. You can take one messy diagonal force, F, and physically tear it into 2 neat, straight pieces, an x-axis piece and a y-axis piece. The side that's hugging the angle theta, that becomes F times cosine theta. The side facing away from the angle, that becomes F times sine theta. Once you shatter all your diagonal vectors into straight horizontal and vertical lines, you just group all your x's together and all your y's together. It literally turns a nightmare geometry puzzle into basic elementary school addition.
Section 5. Vector multiplication basics.
So yes, believe it or not, you actually can multiply directions. Imagine pulling a toy car across the floor with a string. You're kind of pulling up and forward, right? But the car only moves forward along the floor. This means only a fraction of your pull is actually doing the work. The vertical part of your pull, that sine theta part we just looked at, is doing absolutely nothing but trying to lift the car up against gravity. It's totally wasted effort when it comes to forward progress. The only part of your force actually contributing to moving the car is that horizontal component. And this perfectly crystallizes why the cosine is so necessary here. When you take a force vector and multiply it by a displacement vector using what we call the dot product, the formula naturally builds in the cosine of the angle between them. It mathematically filters out and ignores any force that isn't actively helping the object move in its actual direction. The result you're left with isn't even a vector anymore, it's just a clean, pure scalar number representing work. It's such an elegant way for physics to just filter out what matters from what doesn't.
We've totally mastered scalars and the dot product today, but I'm going to leave you with this one final thought. What happens when forces multiply in 3D space and create an entirely new perpendicular directional arrow? Imagine tightening a bolt with a wrench. You pull down, but the bolt moves inward, right? That is 2 directions combining to create a mysterious third, entirely perpendicular direction. That, my friends, is the realm of the cross product, and it proves just how deep and fascinating the rabbit hole of vector mathematics truly goes. But hey, we've unlocked the essentials for today. Take these tools, start viewing the physical world through the lens of magnitudes and directions, and above all, stay intensely curious.